So after this very inspiring talk, I will address more pragmatic matters, and I would like to introduce you to a series of tools based on recurrent neural nets that can be used in order to transform sequences to go from an input sequence to an output sequence. I'm sure that some of you already know RNNs, but I will talk about an application that is less known in this framework, and which is based on time series, and which is time series prediction. What is time series prediction? Well, the idea is that you observe a certain number of values that are time-stamped. This forms your history, and from this history, you want to predict future values, okay? And you can want to predict more than one future value over a certain time span. That is called the horizon. And this is exactly what is called time series prediction or time series forecasting as well. Another application that involves sequence-to-sequence transformation is related to natural language processing. So in natural language processing, we are manipulating strings, and we quite often have to go from input strings to output strings. Machine translation is a very good example for that. So you've got an input string, a sentence in a source language, say English, and then you want to translate it into the French language, so you want to generate another sentence. So here is an example of such a translation that is taken from the NSAT corpus. So the NSAT corpus is the corpus from the Canadian Parliament that was heavily used in the late 80s, early 90s to develop statistical machine translation systems. And you see that here the English sentence is no ifs, no buts, we want the truth. And the French translation is somewhat remote, and it's a very inspired one, to my opinion. The translation is « cessons de tourner autour du pot de chambre ». So no current machine translation system will be able to output that. And the story why did the translator decided on this translation is because it was a debate in the parliament, in the Canadian Parliament, and one deputy in the Canadian Parliament had traveled recently, and he traveled with his butler. And the expenses of the butler were covered by the parliament, which was completely forbidden. Only the expenses of the deputy were supposed to be covered by the parliament. And so there was debate, and some deputies started to argue with the deputy who sort of traveled with his butler and asked him to justify this. And so one said, no ifs, no buts, we want the truth. And the translator, bearing in mind that the translation of butler is valet de chambre, decided to propose this translation. So, of course, there could be more literal translations. For example, we could have said, pas de si, pas de mais, nous voulons la vérité. And this would have been a perfectly correct translation, and this is more reachable, and this is the type of translations that current machine translation systems can find. Another example of transformation from a sequence to another sequence is when you have to generate natural language text. So it's natural language generation. Here I've illustrated it with an input which is called the dialogue act. So in the dialogue act, you have some attributes and some values for each attribute. So for example, for the attribute name, the value will be the eagle, that is a coffee shop, and so on and so forth. And then you want to generate a natural language sentence explaining what is in the dialogue act. So of course, the input here is not really a sequence. Originally, it is a structured input with attribute value pairs. But in fact, in state-of-the-art natural language generation systems, it is just treated as a sequence of characters. Okay, so as I said at the beginning, there is a set of tools based on recurrent neural networks that can be used to generate sequences from other sequences. And I would just like to illustrate how those tools work and how they can be applied in this task, and in particular in time series prediction. So let's assume that we have an input sequence, x1 to xt. How do RNN work? Basically, what they do from this input sequence is they will produce a hidden state for each input. If the input is a sequence of words, it's a text in English, say, each word is typically represented in what is called a one-hot encoding, meaning that it's a huge vector the dimension of which is the size of the vocabulary of your language, and you've got 0 everywhere, but one on the dimension that represents your word. And then from this input representation, you just want to generate those hidden states, which are vectors in a latent space. And the dimensions of these vectors are typically a few hundred. So how is it done? This is done through this phi function that takes as input the current input, as well as the previous hidden state, and will produce the next hidden state. These kind of models, they can be used then in the output to generate another sequence by this, just using the probability, just rewriting the probability of generating a sequence using the chain rule as the probability of generating each symbol at a time based on the previous symbols generated. And this can just be realized from the hidden states, again, by generating a distribution over your whole vocabulary and selecting, normalizing this distribution and selecting the max value. What is this phi function? Well, the phi function, basically, there are two main models that can be used, that are currently used to implement this phi function. That is the function that will give you the hidden states. These two models are the long short-term memory models introduced in '97 by Horheiter and Schmidhuber, and a more recent one, which is called the gated recurrent units, GRU models, introduced by Shaw et al. And in 2014. So here is, I just gave here the mathematical formulation of what's happening in the GRU model. So in this model, as you can see, there are two intermediate variables, ZT and RT. And both of them are based on the current input symbol and the previous hidden state, okay? They're just linear combinations of them plus a sigmoid function and the application of a sigmoid function on the output of this linear combination. You've got another element that is H tilde T, which is basically an activation that will correspond to a standard hidden state in a simple recurrent model. And finally, the hidden state that you have at the end is just a combination of the previous state and this current activation H tilde. So I just want to spend 2 minutes on this slide to illustrate what is this doing. Let's assume that xt, I have a sequence of words. Let's assume, and what I want is just to label this sequence of words with some label indicating whether this belongs to a named entity, a person name, for example, or not. If xt is an empty word, then basically what you want to do is you don't want to have a hidden representation for this word. It has no meaning, it has no influence on the output, so you just want to forget it in a way. You can do that simply by setting zt to 0. In this case, the ht for your empty word will just be the hidden state of the previous word. So you are just passing the information, forgetting this input, which has no impact on the task. On the other hand, if the input marks the beginning of something completely different, and that does not depend on the history, then you want to reactivate everything and forget about what you have memorized in the past. You do that by setting ZT to 1, and this can be learned automatically in these networks. So like that, you see there is a memory process inside that. You can reset your memory, or you can completely forget the input and pass all the information that you had before. Those recurrent neural networks, they're not only used in one direction, but they can be used in 2 directions. And that's something that is called, obviously this is called bidirectional encoders. And this is a nice thing. Why? Because in general, when you have a sentence to translate, you know the complete sentence. If you go just in one direction, you will collect at the last hidden state all the history of that. But then you will also lose some dependencies that may be useful from right to left. When you issue a sentence, you know what you want to say. You know the complete sentence. So the choice of the words that I'm making now also depends on the words that I'm going to make. If you have just a one-directional encoder, you miss that. So people usually use the bidirectional encoder, meaning that you just read the sentence from left to right, and then from right to left. And then you just combine the hidden vectors that you have obtained in both directions. Okay, so this is what's happening on the input side. I've read my sentence, for example, I have encoded it, now I want to produce a translation, say, okay? How am I going to produce this translation? We will try to collect all the hidden states of the input into a single vector, which is called the context vector, and that will be used to generate each word. So in the output. For generating each word in the output, obviously my generation will depend on the previous words that I have generated, as well as on the previous hidden states. So think of the generator as sort of a reverse process from the encoder that we saw before. And this reverse process is coupled with what is called an attention mechanism that allows for each output word to rely on a weighted average of the input hidden vectors. What this means that when I want to generate a particular English word, then I will try to select particular French words to produce this English word. Okay, so that was the short introduction to bidirectional recurrent neural networks, and I will now like to delve a little bit on their application for time series prediction. Some characteristics of time series, of many time series, is that they are multivariate, multiscale. They may or may not contain several periods, depending on seasonality and the underlying patterns. They may or may not contain missing values. State-of-the-art methods currently for time series prediction, they are based on ensemble methods, basically random forest and gradient boosted trees. And I just want to introduce an application of recurrent neural networks in this context. And basically the questions we are asking ourselves are, can recurrent neural networks model periods in time series or pseudo-periods? And are they robust to missing values? We have seen that they have a memory mechanism. Can this memory mechanism be used to encode periods, or so-called pseudo-periods, meaning that there are strong correlations in the input, in the output, in the input? And if yes, is it doing that naturally, or do we have to modify the attention mechanism so as to be able to capture periods? That's basically the question I will address now. This displays the autocorrelation figures for two time series. One which is related to the Polish, which is called the Polish electricity data, which is electric consumptions in different houses in Poland, and another one which is related to weather measurements over a very long period. So the autocorrelation is nice because it shows you the higher the value, the more correlated two data points are. And what we see here is that for the Polish electricity data, the one on the left, there is a clear 1 week period. For the weather data, there is a clear 1 year period. But now, if you just, sorry, I will move to the next one. If you just run recurrent neural network with an attention mechanism, and you look at where the attention weights go, what are the points that are used in order to predict the output, you see this following picture. So for the Polish electricity data, the blue curve is the standard attention mechanism. As you can see, there are more weights paired at the end of the history. Not surprising. When you have to predict next points, if your data is continuous without strong gaps, then it makes sense to rely on the last points you have seen. So this is the assumption that is made. Now, if you just add a position information to your neural networks, say, okay, in addition to the input value, I give the position, and I let my neural network try to capture that, you end up with the curve, the red curve, and which completely misses the period and goes far away from the actual period. And both models, they do not perform very well on this task. So what is missing here? So basically, the attention mechanism is able to capture, to focus on some points in the history, but it will do so by simply comparing the content of these points and the content that it has guessed for generating the output. It's not exactly what you want if you want to capture periods, or pseudo-periods, say. If you want to capture pseudo-periods, what you need is really to be able to say, I want to focus on this particular time difference between my input and my output. Okay? So what you can do is just modify the attention mechanism and simply encode explicitly, add a vector that explicitly encodes this, and combine this vector in the attention mechanism that you have. So let me just recall the previous attention mechanism. So here was the previous attention mechanism, and the weight was based on this EIG, on the equation for EIG. That is, it depends on the hidden state Hj and the previous output states Si-1. And what we are saying now is that it does depend on both of them, right? But it also depends on these elements, pi2 delta ij, blah, 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 that encode the positions, and that forces the model to say, well, I can really focus on these particular time differences and on this particular period in order to predict my output. These are just some illustrations on some data sets. So I've already mentioned the Polish electricity data, the Polish weather. There are also other data sets with, you see the characteristics of this data set with different instances. Different history size, different horizon, and different sampling rates. Here are the results that we obtained. So this is just comparing this mechanism with a period with the original RNN with an attention mechanism, the standard one that you see on the left column, and with two, I will say, very standard methods used for time series prediction. One is ARIMA, and another one is random forest. And you see that on all data sets but one, this mechanism that is able to try to identify periods and rely on them in order to make the prediction outperforms the other elements. And what's happening in terms of the weights that are selected? Well, as you see here, so again, I've shown the weights of the attention mechanism original model, the weights of the attention mechanism with the periods, and you see that for the prediction, there are two clear peaks. One is at 1 day, one is at 7 days. So remember that we are predicting 4 points here. So each peak will be will have a width of 4 points. That's what we observe here. So we are definitely able to capture the 7-day period as well as the 1-day period. And there are other periods that are captured as well, which are less important than the other two. And again, the original model just relies on the last values in order to predict. In a way, it is at a loss where to look for the actual values to help the prediction. And so when you're at a loss, you just rely on the most likely information, the closest one, based on this continuity assumption that I think I mentioned. So I would like to conclude. Currently, there are two state-of-the-art RNNs based on bidirectional long short-term memories or gated recurrent units with an attention mechanism. They can be extended with additional memories, external memories, and there is a research activity around that at the moment, and those models are particularly useful for machine reading. When you have a text to read and you have a system asking you questions on this text, you basically build hidden states for each sentence of the text. So you have all these hidden states for the sentence, attention mechanism, and then you add an extra memory in order to sort of capture the history and the episodes. So, as I said, they are very useful in many applications. But okay, two questions that still remain is, can we do better modeling of long-distance dependencies? And related to the talk given previously by Stéphane Malin, we certainly need a better understanding of these models. Thank you very much.